everyone, welcome to Master 100. So today we are start to look at the first kind of discrete distribution, the binomial distribution. So previously we learned that for discrete random variables, when we don't have many outcomes, and we can always use a distribution table to represent the discrete random variable and study that random variable. But the question now is that what if we have multiple outcomes, say maybe 100 different outcomes. So say, you toss a die 100 times and you keep track of how many 6 appear. At the time, the table itself won't be efficient for you to study, to look at the distribution on the whole. But rather than that, you need a more systematic way to look at the distribution and then its property. And a binomial distribution is the first distribution can help you to manage kind of this large scale of discrete outcomes. So let's move on.
So what is binomial probability distribution? A binomial probability distribution, we write here for short binom prob, which is for probability, and this for distribution, to say space in our slide. So a binomial probability distribution is a distribution. It can be used to model random phenomena that results from procedure that satisfies the 3 following conditions. So first of all, we require the procedure must come from n independent trials. N is a fixed number, is a given number. And then for each trial, the second condition, each trial is only have 2 outcomes, either success or failure. And it should be noticed that the success failure here, it doesn't mean good or bad. It just means the event we care happen or not, right? So for example, like if you toss a die and you check how many 6 appear, right? So at the time, for each toss and you get a 6, which means at the time you get a success. And if you don't get a 6, which is you get a 1, 2, 3, 4, 5, we say we have failure here. And the last condition is that like we require the probability of success or failure for each trial with the same, right? So again, if you toss a die and you care about number 6 appear or not, and success probability would be 1/6, and failure would be 5/6, right? So here another example. You can look at here number of baby girls among 3 different births, right? So at that time, it can be described as a binomial probability distribution. Why? So you can see here all the 3 conditions above satisfy. So first of all, the gender of the baby for each birth are independent, right? They have nothing to do with each other. So basically, like we have 3 independent trials and 3 a fixed number here. And each trial we have 2 outcomes. So in this case, we have either girl or not girl. And the last condition, in this case, the probability of success, which you get a girl, which is 0.5, and failure, which you not get a girl, roughly speaking, also 0.5. So this means like the number of baby girls among 3 different births can be modeled, can be described by binomial distribution. So here's some notation. So a procedure, we have any independent trials, 2 outcomes, each trial success probability P. And if you didn't know X, capital X is a total number of success, and then we say X has a binomial distribution, and we use this notation, X followed by binom NP. So we read that X follow binomial distribution from n trial, independent trial, and success probability P. So if we revisit the number of baby girls among 3 random births here, and we can see that n in our case is 3 because we have 3 independent trials, and P is 0.5 because probably you get a baby girl for each birth, roughly speaking, is 0.5. So the number of baby girls among 3 births will be followed by binom 3.5. Okay. So let's look at this quiz, and then we can have a better understanding about which of the following can be modeled by binomial distribution. So in the first example, roll a die 10 times and track a number appear. Okay. So the experiment here, you roll a die and you track which number appear. Okay. So let's see if it can be modeled by binomial distribution. So we need to check the 3 conditions above, right? So we have n independent trials, the first condition. So in this case, we have 10 thoughts, right? They're all independent, so it met. And n 10, n is 10, and it's fixed number, right? But for the second condition, we require each trial outcome, it has to be either success or failure. So it's basically we have two outcomes. But you can see if you roll a die and then basically like and you track a number appear, right? So at that time you just cannot get that, right? Because you have the 6 outcomes in total when you track number appear. So the second condition violated, which means we cannot model this by a binomial distribution. But how about in B, we roll die 10 times and we track whether number 6 appear or not, right? So at that time, again, the first condition satisfied, but the second, how about second? At that time, you see, we have 2 outcomes, right? Because the thing we care that whether number 6 appear or not. So if 6 appear, we say success. If not, we say failure. So at that time, the second condition satisfied. In the third condition, the probability of success or failure for each trial the same. At the time, it also satisfies because the probability you get a 6 will be 1/6, right? And then the probability you not get a 6 will be 5/6. So which is the last condition satisfied. So in B, it can be modeled by binomial distribution. How about C? You roll a die. Do you see the first 6? Okay, so at the time, let's look at. So the first condition, we require n independent trials and n is a fixed number, right? But think about this random phenomenon. You toss a die and you will stop, right? Till you see the first 6. So maybe sometimes you just touch one time, you get a 6 and you stop, right? But sometimes you maybe need to toss maybe 10 times to get the first 6. But maybe one beautiful day, you do 1,000 times and you didn't see a 6. So at that time, you can see here, in this case, the first condition violated because we don't have the n fixed here, okay? We don't know what is the n. So this cannot be modeled by a binomial distribution. How about D? You randomly choose 10 drivers and track if the driver drunk, okay? So at that time, you can think that you're a policeman, right? And you just go outside and you go to each corner of the street, 10 different random streets you choose, and you check if the driver drunk or not, right? So let's see if it can be modeled by the binomial or not. So in this case, we have n independent trials and fixed, right? N is 10, you track 10 random drivers, and this person drunk or not drunk, it has nothing to do with the other person, right? Each trial has 2 outcomes, good, because a driver can be drunk or not drunk, right? How about the probability of success or failure for each trial the same? So think about that, okay? So in this case, the answer can be yes and no, okay? So the answer will be yes if you think about like, there's some thing right this world where, people get drunk with a certain probability P, and then people not get drunk with probability 1 - P, right? So if you randomly choose like a person, since that person has the probability getting drunk will be P, and not drunk will be 1 - P, right? So if you look at the world this way, and at that time, the number of people get drunk among 10 randomly chosen drivers can be modeled by a binomial distribution. But if you look at in detail, you may wonder, if maybe a young man and a very old man, right? Their probability of getting drunk will be different, right? So if you check a young man, maybe more likely he have a higher probability of getting drunk compared to a very old man, right? And maybe a man and a woman. So at that time, the third condition will be violated. So for this example, we can see that it really depends on how you look at the world, right? Sometimes you just look at in too much detail, and basically you just stuck there. You cannot do anything else. You cannot move any further to study that. But if you look at it more in a more flexibility way, and then at the time you can model that and you can start to study the random phenomenon. So the answer for D is yes and no. It just depends how you look at it, right? You look at it. So let's talk about the properties of the binomial distribution. Okay, and this is a beauty when you start to learn the distribution of a discrete random variable in a systematic way. Okay, so say if x follow a binomial distribution with n and p, you can know that all the value x can take will be from either 0, 1, 2 to n. Okay, and the property of we get a k success. It is given by this formula. Choose k from n, p to the k and 1 minus p to the n minus k. And sometimes people, they didn't know the 1 minus p by q, but I just try to avoid make use too much notation here. Okay, and choose k to the n. You learn already in your high school, which is the n factorial divided by k factorial times n minus k factorial. But the good thing here is that like actually your TI calculator have a function to do this calculation for you. Okay, which is binomial PDF function. Okay, we look at it very soon in next slide. And with binomial distribution, you can know that the mean is given by this formula n times p. Okay, it can be proved easily, but it's not the scope of this class, so we just accept it as a fact. Okay, and the variance, people, they also can prove that it is n p times 1 minus p. Okay, and because it's a variance, so you can get a standard deviation, which is square root of np 1 minus p here. Okay, so pretty much like if you can model a random phenomenon by binomial distribution, and then you just know everything about that, right? The range of the value, the probability that your random variable equal to a certain given value, the mean, the variance. Okay, so let's look at this example, right? So again, we look at when you toss a die 10 times and you keep a track number of 6 appears. So that time we already discussed in the B here, right? Which it can be random model by a binomial distribution. In this case, our binomial would be 10.167, okay? Because 0.167, which is the probability getting a 6, which is 1 over 6 here, okay? And n is 10 because we toss die 10 times, okay? So from here, you can calculate the exact property, right? So what the property? I get 2, 6 in 10 toss, right? So which is px equal 2. So for sure, you can use the formula here, which is choose 2 to the 6 and p to the 2, 1 minus p to the 6 subtract 2, right? But don't do that, okay? Use this function, binomial PDF 10.167, 2, okay? So let me show you how to do that on the TI calculator here. So the property, you get 2, 6, right? Among 10 toss. TI for sage count. Okay, so go to test snap here. Start, and then choose a calculator in the middle here. You do second, then distribution here. You go down to binomial PDF, okay, binomial PDF. So you have 10 trials because you toss the die 10 times. Your success probability is 0.167. This is the probability you get a 6, right? And you get the x value 2 because you want to calculate the probability. You get 2, 6, okay? And you paste it and enter again. So you can see here we get 0.291. So which means the probability you get 2, 6 among 10 toss will be 0.291, okay? This is a binomial PDF function. Binomial probability distribution function, okay? And it the short version of this binomial PDF, okay? How about we find the probability get at most 2 number 6, right? Get number 6 at most 2 times, right? So which means probability x equal less than equal to 2, okay? At most 2 times. So which means you can get the 0, 6, 1, 6, 2, 6, right? So here we say at most 2 times. So at the time, in order to calculate this probability x equal less than 2, less than equal 2, so you can go in the, you can use a binomial PDF, do it manually like previously, right? So you consider like probability x equal less than equal 2 equal to probability x equal 0 plus probability x equal 1 plus probability x equal 2, right? And then other time you just do binomial PDF 10.1670 plus binomial PDF 10.1671 and plus binomial PDF 10.1672, and you get the answer, right? But the good thing here is that LTI have another function we call binomial CDF, okay, which means binomial cumulative distribution function. So this function, it will help you calculate all the probability up to this point, okay? So in this case, if you do like binomial CDF 10.1672, it will give you everything up to 2, okay? So again, you can also plug it in the calculator and you see it, okay? So this here, right? You do second here, distribution, binomial CDF. Binomial CDF, okay? So be careful with these two functions, okay? So each of them had a different purpose. The CDF, it calculate everything up to the value, right? 0.167, which is a set probability up to 2, right? Everything up to 2. Okay. So in this case, it will be 0.774. Okay, 0.774. I'm sorry. But previously, it's only 0.291 because previously it's just a probability x equal 2, right? But now probability x less than equal 2. Okay. So this is a difference between binomial CDF and binomial PDF. So again, so let's look at the number of baby girls about among 3 births again, okay? So you can see that this can be modeled by a binomial distribution, right? So other than the number of baby girls among 3 births, it can be modeled by a binomial from 3, n equal 3 and success probability 0.5, right? So you can see that if we model that, we are able to model that, right? So we use this slide, okay, the properties here, and we see that we know everything about this random phenomenon, right? How it distributed. We know that, okay, the number of baby girls among 3 births, it must be between either 0, 1, 2, or 3, right? And you also know what the probability you get 0 baby girl, which is binomial PDF 3.50, and you use a calculator, you should get 0.125. Well, the probability you get a 1 baby girl among 3 births, right? Which is 0.375. What probability you get 2 baby girls, right? Either time you just do binomial PDF at 2, you get 0.375. And what the probability you get 3 baby girls, right? Also 0.125. You also can calculate what the mean, right? Value, right? So if what the mean value for this random phenomenon, okay? So say, if the whole cluster, right? If you just randomly choose 3 new births, right, and check the number of baby girls, and basically like the average of the whole class get will be 0.15. And we can also get the sigma square, which is the variance, which in this case, using the formula, right, n times p 1 minus p, and you get this 0.75, and you can also calculate standard deviation, which is square root of 0.75, you get 0.866. So you see, now you know everything about this, how this random phenomenon distributed, right? Distributed. So look at another example. So here, like, based on a poll, it said that 82% of U.S. adults want United Nations has quarter, we know UNH, they remain in the U.S. Okay, so now we randomly selected 10 U.S. adults. Okay, and we know X is the number of people who want the UNH remain in the U.S. Okay, so find the following probability. What probability we had like more than at least 4 people, right? X less than equal 4, X greater than equal 4, at least 4 people. One UNH remaining in the US. And then B, probably the number of people want UNH remain in the USE from 3 to 5, then from 3 to 9, and also mean and standardization of the X here, okay? So let's walk through this problem part by part, okay? So for part A, okay, we want to find probably like X greater than equal than 4, right? So here again, first of all, before we process the problem, we should model it by a binomial distribution, right? We should check if we can model it by binomial distribution or not, right? So say because you randomly select 10 US those, so basically we have 10 independent trials already, which is the first condition. The second condition, the outcome, we have two outcomes, right? People either want UNH remain here or not, right? And the third condition, which is probably success and failure the same for each trial, right? So again, here, because we have 82% of US adults want UNH remain in the US, which is the underlying truth given to us. So which means like probably success, which means you randomly choose person and you ask him or her if you want UNH remain here. And we get the probability he or she want UNH remain here 0.28, A2, right? A2. So which means at the time you can model it by a binomial distribution n 0.82, okay? And after you have that, right? And everything now will be, follow the normal binomial calculation easily, okay? So let's first of all talk about what the property we have at least for people want UNH remain here, okay? When you randomly survey 4 people, 10 people, okay? So at the time you can see that one way you can do that is that, you just probably X less greater than or equal than 4 will be equal to probably X equal 4 plus probably X equal 5 plus probably X equal 6, 7, 8, 9, and 10. And for each of them, you do binomial PDF, okay? But if you do that, it will be very time consuming, right? And it won't be efficient because say if you survey maybe 1,000 people and at a time, this will be not doable, right? Not feasible for you to do that manually. So we think about a smarter way to do that by using the complement strategy, right? So X greater than or equal than 4 is the complement of X less than 4, right? X less than 4. So at least 4 people, which means less is a complement of less than 4 people, right? Less than 4 people. So which is probably X greater than or equal than 4 will be equal to 1 subtract the probably X less than 4, okay? There's a complement rule we did learn in chapter 3. These two events here, they opposite, right? They complement each other and they make the whole sample space, okay? But because if you just keep this here like this, you cannot block in your TI, right? Your TI, the binomial CDF function, it requires less than equal, okay? Less than equal. The binomial CDF function, it requires the less than or equal sign, okay? Less than equal. So which means here, you just, when X less than 4, right? And X is a number of people, like 1 UNH remain here. X less than 4, which means X from 3 and below, right? Which is almost 3, right? Almost 3. So here we just rewrite this by using, less than 4, which means equal to less than equal 3, okay? And less than equal 3 is just a binomial CDF function, right? You should do binomial CDF 10.28 and 3. Another time, if you plug in your TI calculator, you should be able to get this quantity, 0.995, okay? So the property of, we have at least 4 people, right? At least 4 people. One UNH remain here, 0.9995, okay? 995. And let's look at the B, okay? What the property we get like from 3 to 5 people, 1 UNH remain here, okay? So the first strategy is that we just try to break it out from 3 to 5, which means either 3 or 4 or 5, right? And we use binomial PDF for each of them. Binomial PDF at 3, binomial PDF at 4, binomial PDF at 5. And this is the property you get, right? So property you get from, if you randomly survey 10 people, and they are about from 3 to 5 people, one UNH remain here, 1, 2, 1, 3. But there another way you can play around, and often it's more efficient, is that you use this strategy, okay? So x less than or equal than 5 and greater than equal 3 will be equal to probably x less than equal 5, subtract probably x less than equal 2, okay? Less than equal 2. Think about it, okay? And then like for x less than equal 5, you just use binomial CDF at 5 and subtract binomial CDF at 2, and you also get the same result, okay? So what is the case here? So let me explain it a bit further for you. In this case, let me just make another slide here. Okay. Use here, okay. So part B, right? B. Okay. S 5, right? 3. Y. So our question is that why is the case here? Right? So the x less than equal 5. So this event, basically this event equal to like 3, 4, 5, right? Which means x belong to this. How about this event? This event is x less than equal 5, which means x belong to 0, 1, 2, 3, 4, 5, right? And how about this event? X less than equal 2, which means x belong to 0, 1, 2, right? So see, if you subtract this event, right, to this event, right? So the remaining you get will be this, right? Because it had a 0, 1, 2 in common, right? 3, 4, 5, okay? So which means exactly is the same. It's the same here, right? Another way you can look at it is that you can use this relation here. 3 and 5 equal to probably x less than 5. Subtract, okay, x less than 3, okay? Less than 3. And again, x less than 3 and x is integer number. So basically it's x 2, okay? Notice that x is an integer, okay? Integer, right? So either way, this is how you make this transformation work, okay? And for each of them here, it's just a binomial CDF, right? We just saw it. Okay, so either way, way 1, way 2 work, right? But now you should be able to appreciate the way number 2, right? The strategy, it's the smarter strategy, and we just did by doing a little bit transformation, okay? So here, while the property, the number of people, 1 unit remain in the US between 3 and 9, okay? So now we replace the number 5 by number 9. So for sure, if you see, you want to process in the way number 1, then you need to do probably x equal 3, 4, 5, 6, 7, 8, 9, right? So it's very time consuming, okay? So imagine the case, say, you survey 1,000 people, right? And you want to find probably like the number of people want you and it remain here from 300 to 900, something like that, right? And for sure, if you follow the way number 1, it will hurt you, right? But now, if you follow way number 2, this is nothing else than probably x less than equal 9, subtract probably x less than equal 2, right? Just the same thing, right? The same thing. And at that time, you can just do binomial CDF 10.82, 9, subtract binomial CDF 10.822, right? So here like the 9 is replace the 5 in previous part, right? In part B here. C we have a 9. And other time you get a 0.863, which is this probability. So it's much more efficient if you follow this strategy. And the last part is that find the expected value and the standard deviation of x, right? So we do have formula for that. Expected value will be n times p here, mean, right? The mean n times p. And the standard deviation is just the square root of this quantity. And n in our case is 10 and p is 0.28, 0.82, right? So we can find ex n times p equal 8.2 and standard deviation of x equal to 10 times 0.282 and 1 subtract 0.82 and you get, after you do a calculation, this number you get, okay? So we finished the example 423. So let's just look at an application, okay, in real life. This is, from the airline business, okay, which we call airline booking, okay. So here are the facts, okay. So airlines, they often sell more tickets than seats to optimize the revenue. And why is the case here? So airline industry, they do keep track the empirical data about the people that, who do the last minute cancel or did not show up, right? So here we assume that the data is give us, based on the empirical data, the last minute cancel is probably 0.07. Okay. And other, the last minute cancel, it causes the airline sometimes in trouble because sometimes they get a very high substantial amount of refund. And also say, if they don't get a refund, right? But say basically the airline, they will waste the seat, right? The seat, and they cannot optimize their air revenue. So here, this is why they think about how to try to fill up as much seat as they can, and also avoid the problem, when two people show up and one of them cannot fly, right? So here, like, let's look at the example, like the Delta Boeing 747. It had a 456. It fly from San Francisco to Ho Chi Minh City, which is SGN in Vietnam, okay, airport. So if they have 456, okay, so they may consider selling maybe 460 to 500 tickets, okay. They don't sell exactly 450, but they do sell more. Maybe, I'm not sure which number. They have an algorithm to find out which one is the optimized number they should sell, okay. But often they oversell those the number of tickets, okay. So for example, like, they sell 1,500 per ticket, right? And if like we have more passengers show up, right, and some cannot fly, and they should have some compensation, right? So refund and give the hotel. So totally cost maybe 2,000. This is the phenomenon, okay? This is the case study, okay? So so you see, you understand the process, right? So this is so basically this is a business here, okay? They only have 456, but they do sell 460 to 500 tickets, okay? For example, like 1,000. If we have like $1,500 per ticket, but say if more passengers show up, right? Some cannot fly, and the one who cannot fly, they need they get a refund and some compensation, right? Compensation. So we are, because from empirical data, right, we have like the number of passengers, the probability passengers show up will be 0.93, right? Because the last minute cancel is 0.07, so which means the show up will be 0.93, right? And say if say Delta, let's look at the first scenario, okay? If Delta they sell 460 tickets, okay, what happened? Okay, so here for the airline business, if they do sell 460 tickets, so what they care about? They will care about how many people is going to show up, right? If they sell 460 tickets, right? 460 tickets. And to study that, they need to model it some way, right? Somehow, right? So here, like to make it work, first, you think like you sell 460 tickets. You may assume, okay, because the ticket just sell to random people, right? So you can think, you can assume, make assumption, independent assumption here. So one person cancel or not cancel, it has nothing to do with the other person. Now, for sure, in real life, it may not true because some people, they travel by group or family, right? They go together. So if one person cancel, the whole cancel. But if again, if you're not so flexible here, you cannot do much, right? You just stuck there. So basically here we can just assume, okay, the passengers show ups are not each independent event, right? One has nothing to do with each other. So I think like it's quite okay for this case, okay. And then like the second condition where we require two outcomes, right? So people either show up or not show up. So we have two outcomes. And then the last one, probably success, a failure would be the same, right? So success, which means 0.93. In this case, we care about how many people show up, right? And failure 0.07, right? So basically, if that's the case, and then you can model, right? The number of people show up, follow a binomial for 60 and 0.93, okay, 0.93. So we have 460 independent trial, which is 460 tickets, right? People show up and 460 tickets, right? And then the probably show up 8.93, right? So for airline ticket, why we care when we do that? Because we only have 456, right? So we do care about the event probably X greater than 450, right? We want to know is it a big number or small number? If it's a big number, we don't want to mess with that case, right? Because if so many people show up and the number of people show up with more than the seat we have, right? Behind the number of high probability, and then at the time, you often in big trouble because if it often too frequently, and beside the compensation you pay out, you also lost your reputation, right? And then maybe they will never fly with you again. So we do care about what probably number of people show up greater than number of seats available, right? Which is probably X greater than 450, okay, 450. So at the time, again, we just use the complement strategy, right? X greater than 450, which is 1 subtract X less than equal 450, right? And then probably X less than equal 450, again, it's just a binomial CDF function, right? At most 450 is show up, right? So let's calculate this probability and see. So the calculation show here is 0.00077. So which means a very small probability, right? So let's just redo it and see if we can get this number. Which is 1 subtract binomial CDF. We have 460 tickets sold, right? We have success probability, we put probability 0.93. And we have the value here, we care at most 450, okay? So 1 subtract binomial CDF 460, 0.93, and 450, right? So you see this exact number we get in the slide, okay? So very small probability this can happen if you sell 460 tickets. So we should go for that, right? 460 should be a good starting point, okay? Because this it seems unlikely to happen, right? It's very small. How about you are greedy, right? You do business, you want to get more revenue, and then say, oh, I will sell 500 tickets, okay, to make the revenue, to increase the revenue. So that time, the number of people show up, it again, the same strategy, right? But now it can be modeled by binomial 500.93, right? Because you did sell 500 tickets, right? So number of people show up, and we have 500 independent trial. Here we assume independent between show up, right? we have two outcomes, show up and not show up, with show up probability fixed, which is 0.93, right? So that time, again, we do care about what probability we get in trouble, right? Which is like we have more than 450 people show up. So you just do the same strategy, 1 subtract probability x greater than 450 equal to 1 subtract probability x less than equal 450. And you do a binomial CDF 500, 493, and 450, right? 1 subtract that quantity, and this is the quantity you get, right? 0.992, 0.992. So which is very high probability. So it's better we shouldn't do that, right? Because it's often the case we get the embarrassment, right? Embarrassment and with the customers, right? And because some cannot fly, and you know, if some customer they really want to fly, and you know they're angry, and you know a lot of consequence can happen, right? A lot of consequence can happen. So actually in real life, there are some optimization algorithm, okay? They can use to get what is the optimized number they should decide, right? For 60 or for 70 to maximize the revenue. Also, you know, they try to not like get embarrassed embarrassed by the angry from the customer, right? So here we see an application of the binomial distribution in the real life problem, okay, in the airline overbooking, okay. So let's talk about this quiz, okay. So here, this in quality control, people often do that, okay. So here we have a company, they make 1,000 rubber, okay. And suppose in fact 7 of them defective, okay. And since we cannot test the entire batch, okay, so quality control, they randomly choose a mini batch of 6 ducks and test, okay, 6 ducks and test. If all mini batch is good, the entire batch can be shipped, okay, can be shipped. So they cannot do for all 1,000, so they just do for 6 ducks, randomly chosen duck, okay. So if all mini batch is good, the entire batch can be shipped, okay. So find the property, the entire batch can be shipped, okay. And at least 1 duck in the mini batch defective, which is number B, part P, and part C, number of defective duck between 3 and 5, okay. So let's look at this problem part by part, okay. Let me insert a slide. So you have 1,000 rubber ducks, right? And the truth here that like 7 of them defective. Okay. So which means the defective probability is 7 out of 1,000, right? 0.007 here. Okay. And the thing here that you just randomly choose 6 ducks and test, right? 6 ducks and test, right? And if all mini batch is good, the entire batch can be shipped, right? So in A, you find the probability entire batch, which is the whole 1,000 duck, can be shipped, right? Can be shipped. Okay. So which means it is the probability. So entire batch can be shipped if all mini batch is good, right? So which is the probability? All ducks in the mini batch is good, right? Is good. Eh? In the mini batch, we have 6 ducks, right? You know that? In the mini batch, we have 6 ducks, right? 6 ducks. Okay. We have 6 ducks in the mini batch, right? So from here you can see that what we care about all ducks in the mini batch is good, right? And if we know X is the number of maybe good duck, right? Good duck. You can define good duck or defective duck. It depends on the event you define, okay? So here, number of defective duck, okay? Defective duck. So here the success means you get a defective duck, okay? In the mini batch, okay? Okay. So at a time, if you didn't know X is the number of defective duck in the mini batch and you have 6 ducks in the mini batch, okay? And at a time, because the sample size here is too small compared to the whole population, which is 6 compared to 1,000, it's much less than 5%. So you can think like the event is duck in the mini batch, defective or not, it had nothing to do with the other one. So you have like 6 independent trial, okay? So which means the first condition of binomial satisfied. The second condition, which is either you have a defective duck or not defective duck, which is you have 2 outcomes, right? And the probability defective will be success, right? Defective duck, get defective duck, you can think it's just fixed, which is 0.07 here for each trial, okay? And the reason we can do that is that like the sample size is too small compared to the whole population, okay? The population size. So the rule of thumb is that if the sample size less than 5% of population size, and at that time, the event independent probability and the probability of fixed success for each trial will be met, okay? It's reasonable to assume that, okay? So in this case, X we can model by binomial 6, okay, 0.07, okay? So 6 is, which means we have 6 ducks is tested, right? And it has a success probability, which is we find defective is 0.07, okay? So we come back to our part A problem. The entire batch can be shipped equal to probably all ducks in the mini batch good, right? So which means equal to, so we write it here and here. Entire batch can be shipped equal to all ducks in the mini batch is good. Good, right? Equal to the number defective in the mini batch is 0, right? Because if we don't have any defective, which means all duck in the mini batch is good, right? So at that time, you can see we just do a binomial PDF function. PDF 6.07 and 0. Okay. So what is the answer here? We'll leave it for the quiz today, okay? For the quiz today. We do have web quiz. So please, use the TI calculator, find this number, and get the answer for part A, okay? And for part B, let me insert another slide. B. Find the probability that at least one duck in the mini batch is defective, at least one event, right? Which is probability X, at least one, right? Which is X, at least one duck is defective, right? We care about defective. So at the time, the at least one event, again, we don't deal with that directly, right? We will do the complement strategy, which is X less than 1, right? And which is 1 subtract px equals 0, right? Because x is the number of defective duct and x has to be integer. If it's less than 1, it can only be 0, right? We don't have negative thing here. And probably x equals 0, just like what we got in A, right? So basically just 1 subtract to whatever you got in part A, right? 1 subtract to whatever you got in part A, right? From part A here, part A. Okay, plug in. Okay. Okay. So again, the quiz 422 is the pub quiz for today. So please do the calculation and give me a number here, okay? And see number of defective duct between 3 and 5, right? 3 and 5. So in this case, again, it just come back to the UNH type problem, right? X, 3, and 5. So we can do it by using x equals 3 plus 4 plus 5. But I suggest using this strategy, right? Subtract x less than equal to. So in this case, it's just a binomial CDF 6.0075 subtract binomial CDF 6.0072. And this is your job, okay? Okay. So this will be the quiz, pub quiz for today's class, okay?
So we have finished the binomial distribution. So you can see that it is a very powerful distribution to model the discrete random variable in a very systematic way. It's much more powerful compared to what we see in the probability distribution table. And we did see a real life application of this distribution in the business of airline, right? When airline they use the overbooking strategy to maximize their revenue.